So, if I remember correctly, my talk is going to be about some Liouville type theorems. So, the idea mostly is that if you want to prove Liouville, so let me quickly remind you what the standard statement for Liouville is, and I am going to mostly restrict myself to the Laplacian. You can do all of this for, so yeah, two sort of, I guess, generalizations are as follows. One, you can easily use an elliptic operator here, uniformly elliptic. But then somebody will tell you, oh, but if you use a uniformly elliptic operator, then it's the Laplacian on some manifold. So, okay, fine. So everything is as good as the Laplacian for all intents and purposes. Also, you can consider weak solutions in the sense that everyone here definitely knows what I mean when I say you can take objects in a Sobolev space. So in a weak, in H1, so Luca apparently is not familiar with Sobolev spaces, but I will give you a book later. Some references, yeah, right. So everything can be done weakly, but you know, don't. That's working too hard for something that's not so hard after all. Right? Okay, so Liouville type theorems for me are all global theorems. So in particular, you're considering these things globally, right? And so the classical one looks like this, right? So the classical Liouville theorem goes, if U is bounded, then U is constant, right? The proof, there are many proofs. In fact, some of the stuff I'll show today are proofs of this statement. Of course, the one that I think, you know, you can, again, you can either use some kind of representation formula and use like the mean value theorem for the derivative and blah de blah, or you can use, so I guess, let me see, so the mean value property can get you there. And more importantly, Harmonic inequality can get you there. Okay. The problem is that these all rely on equality in the equation. I'll call this star. So they all rely on the fact that this is actually a solution, that the Laplacian is identically 0, pointwise 0 everywhere. So one question that you can ask is, what about subsolutions? So of course it suffices to think about subsolutions because you take a minus and everything is linear, so it automatically says something about supersolutions. So what about subsolutions? And again, just to clarify, that means the Laplacian is non-negative. So notice that Harmonic inequality no longer exists. There is no Harmonic inequality for subsolutions. There is also a mean value property, but it's an inequality. Which, of course, if you look at the mean value property for harmonic functions, the way you prove that, or prove this rather, is by taking a derivative and saying, hey, the derivative decays like something, and therefore is 0, and then therefore it's constant. Of course, that means it is 0, equals 0. This will just show you that the derivative is less than 0 now, because it's a subsolution, or bigger than 0, or whatever. So it's an inequality, and so you don't get that the derivative is 0. You just get an inequality for the derivative. And as I said, there is no Harmonic inequality, so you can't do a sup is less than inf, but the inf is as small as you want, so then it's 0 kind of argument. So, so the question is, are there any Liouville theorems and Liouville type theorems? And the answer is sometimes. Depends. The funny thing, however, and maybe this is going to be the, you know, oh what kind of aspect of my talk, is that everything kind of works in 2 dimensions, not higher. Okay, so sometimes and mostly when n equal 2. So that n is, by the way, the dimension of the ambient space. Okay? Let me start off with a simple example. Of course, oh, by the way, so this is bounded. It can also be bounded above or below. It really doesn't matter. It doesn't have to be bounded from both ends. It doesn't have to be sandwiched. It can be on one half or the other, and that's fine. Of course, you can always translate these suckers, right? Because you can always add something, and that doesn't affect the equation. So you might as well always assume that these things are non-negative, for example. Okay, so do you want me to go to this board at all? All right, so let me start with something silly. So again, I'll be in 2 dimensions for the most part. So this is my first theorem of the day. Hopefully I'll get to something a little more interesting, but this is one of my sort of favorite proofs. So if you take the Laplacian, but now you have a subsolution, all right? As I said, I'll restrict to 2 dimensions. And I will also assume that U is bounded from above. Okay? The claim is that U is constant. Okay. Before I prove this, let me make a few remarks. So, a couple of remarks are in order. One is that a lower bound on U is useless because U equals x squared is a completely nice function. That is, of course, a subsolution, right? Satisfies Laplacian of U is what now? So it's 2, right? No, it's 4. Whatever, it's bigger than 0. Okay? Take 2 derivatives and add 2 plus 2. So yeah, okay, fine, it's 4. And it's bigger than 0. Okay? In 2 dimensions, it's 4. In n dimensions, it's 2n. So this is obviously not negative, obviously unbounded. Obviously not constant, in fact, is more important. Okay? So a lower bound is no good. So this is, but of course U is non-negative. So a lower bound is no good. You need an upper bound. Okay? All right, number 2 is that, as I said, a lot of these things don't work in higher dimensions, and this is another one of these equations that fails to generalize to higher dimensions. So remark number 2 is that the theorem is false if n is greater than or equal to 3. In fact, there are examples of the following form.
You need a lower bound if you take the supers, no? If U is super.
Yeah, other way around.
Yeah, exactly. Otherwise,
yeah, but this is a sub-solution.
Yes.
Lower bound. That's what I was trying to access. In higher dimensions, none of this stuff works. So there is, I mean, this is overkill. You can cook up a function quite easily in higher dimensions. But let me just mention this because this might actually provide fodder for somebody else, or maybe I'll do it myself someday. So this is in some sense a quick aside that's related to this. But this thing here is goes by many names. It's sometimes called the Lane-Emden-Fowler equation. Okay. This turns out to be a critical equation in this family. So this is critical for critical exponent here. So the critical exponent turns out to be n plus 2 over n minus 2. Why is it critical? Because it turns out if the p is bigger than this, there are no solutions. And if the p is smaller, then you can prove solutions exist by sort of standard variational methods. I won't really get into that at all. It turns out to be hard to prove stuff for the critical case. Okay, but There is a deep result of Gitas, Nie, and Nuremberg that says the following. It says that this up here. So if you really want to call this a theorem, you can call it a theorem. That if you take a global solution, so a global solution to this problem, in Rn, of course n is bigger than 3, and U is like the fundamental solution of the Laplacian at infinity, okay, and positive. Okay, so if you consider a solution of this global problem, right, it turns out that U must in fact be radial. So you have to have rotational symmetry, and the U's are basically of this form. They look like, let me make sure I get the exponents right, but they look like this. Okay, and again, why would that work? Why is this even a solution you would think of? The way you get your hands on this guy is by assuming that the solution is radial and turning this into an ODE. Then you solve the ODE and you get this. Okay? But first you have to prove radial symmetry, and that is actually the deep part of the theorem. Okay? But once you prove radial symmetry, that has to be the only solution. Let me throw down a few words that are, nowadays standard. The proof is actually maybe the first instance of the method of moving planes. And I will not mention anything about this because it has nothing to do with my talk. But if anyone's interested, look it up. And I have some stuff that I can show you about that. Okay, what was the damn point of this? Look, if you take a positive solution like that, of course, this guy is non-negative, yeah? And that guy has a lower bound, it's also non-negative. So flip it around, take minus, and you'll find a super solution, the sub-solution that's bounded from above, clearly, and is non-trivial. Okay, does that make sense? So just take minus this guy. So remember there's a minus sign in front of the Laplacian. So if you throw the minus inside, minus U satisfies Laplacian is non-negative, and minus U is non-positive. So it's bounded from above by 0. So in the case C is 0, that works. All good?
Okay.
So these provide an entire family of counterexamples. So why do I say entire family? The family in the dimension. For each dimension, there's a counterexample. Okay. All right. So again, this was not really the point. The point was that. So maybe I'll write this here. False if n is bigger than or equal to 3. Okay. So let's get to the proof. Why false? And what exactly about n equal 2 are you using, which results in a proof? And the proof is like stupid easy, except it's not, in the sense that, it's one of these tricks that you look at and you're like, oh, okay, who came up with that idea? But again, that's kind of the point of the seminar, right? Show some non-standard tricks and techniques and so forth. All right, so here's the proof. So the point really is this, that if you take, I'll call this V epsilon, so take epsilon, fix it on some positive epsilon, and consider the following function. V epsilon is U plus epsilon log x. This is all two-dimensional, right? So why would you do this? So recall that this is, in fact, this is the fundamental solution of the Laplacian. the thing is, I won't actually use the fundamental solution characterization of this. I will simply use the fact that two observations, rather, not they're facts and observations. One is that log x vanishes on the unit circle, obviously, unlike what many calc students think. Two is that it is unbounded at infinity. And that's important. Okay, it's unbounded. In fact, it's unbounded in a sort of negative way. So outside the unit disk, which is here, let's say, log is simply a function that does that. Log of x is simply a function that I guess I should put minus, right? Yeah. Okay. So minus log x looks like that, right? So this is. Okay. All right. So here's the thing. Notice that the Laplacian of v epsilon is clearly non-negative. Why? Because the log part just goes away, right? And by assumption, this was Laplacian is bigger than 0. Okay? All right, for each epsilon, in fact. Also, v epsilon restricted to the unit circle is simply u. Everywhere. Well, okay, outside, you know. Yeah, outside 0.
I don't know if it's important.
It's not important. It's outside the so for, let's say, for x bigger than or equal to 1. Okay. So that's for sure, right? Outside the unit disk. I'm not worried about inside yet. I'm going to go inside later, but right now I'm worried about the outside. Okay? And of course, it restricts to the disk, to the boundary, and gives you u back because, well, the log doesn't count for anything based on these two observations. Agreed? Okay, so here's the point. For epsilon given, there exists some r epsilon bigger than 0, such that if you take any r bigger than that epsilon, r epsilon, sorry, then u restricted to x equals r, sorry, not u, v epsilon, is, well, let's say, less than the maximum of u on the unit circle. So the picture again is this, that you take a super large annulus. So here's the unit disk, and here's a giant annulus. And what's the point of this annulus? Well, this goes off to negative infinity. So if you take a sufficiently large enough radius, this is going to start counting negatively. This, on the other hand, is bounded above. So it can only contribute so much. After a point, you have to become very negative. Also, you can make sure that you're negative enough to beat the maximum on this guy. Again, the maximum on this, it's a compact set. It's nice and bounded. So if you pick a radius sufficiently large, you can ensure this is true. You agree? So it's just going super far away from the unit disk. Okay, what does that really imply? Well, if you look at this guy now, let me erase some of this. Okay, so what was the point of that? The point of that was that right, so the point of that was was the following. You're smaller than the max on the unit circle, but of course on the unit circle you're exactly the same function. Why? Because of this. Right? So here is a subharmonic function on a giant annulus whose maximum is clearly on the inner ring. Okay? If you go too far out, you become too negative, and so your maximum gets smaller than the maximum inside. Conclusion, by the maximum principle for subharmonic functions, the max on the entire annulus of V epsilon is in fact the max, well, not just the entire annulus, but outside the unit disk, is the max on the inner ring, which of course is just the max of U. Why do I write it this way? Because this is independent of epsilon. You see that? So if you now let epsilon go to 0, then you get that the max on the outside of U is the max on the boundary. Okay? Everything makes sense? So, everything so far has been outside the unit disk. All I proved was that the maximum outside the unit disk is in fact the maximum on the boundary of the unit disk. Okay? So the outside doesn't count for anything, basically, is what I'm saying. All right, how do you turn this into a statement about the inside? Well, nobody said you can't use the maximum principle twice. The maximum principle applied to the disk tells you that the maximum on the disk is also on the boundary. Okay, so the maximum principle on x less than 1 implies the max on the unit disk is also the max on the boundary. You agree? So, what was the punchline? The max in all of Rn, or R2 rather, is the max on the boundary. Does anyone see an immediate contradiction here? Or rather, what's the conclusion? Why? Well, okay, so rather it's the strong maximum principle.
Okay.
So strong maximum principle tells you implies U is constant. Because you can't have an interior max, that's the thing. So in Rn, the max is on the boundary of the disk. If you take the 2-ball, for example, then you have an interior max in the 2-ball, which of course violates.
About the epsilon, sorry.
The V epsilon is for this.
The max on the outside.
The V epsilon is to conclude that this is true. The max outside the disk is on the boundary.
Oh, yeah.
Then you use maximum principle inside. Then you get the maximum everywhere. No, I don't need that. Yeah, I don't need that here.
And you get that the maximum is on x equal to 1. That is impossible for the maximum for the strong maximum principle.
Yeah, exactly. That's it.
Okay.
Okay. You might wonder, why would this proof fail in higher dimensions? Well, the problem is that the fundamental solution in higher dimensions doesn't look like log. It looks like some negative power of x, which of course does not go to negative infinity at infinity. So it doesn't help. Right? This is one of many instances I've come upon since looking at this proof where that characterization of the fundamental solution has proved to be absolutely crucial to an argument for two-dimensional theorems that don't apply to 3 dimensions. All right, any questions on that proof? So this is by far one of the cutest proofs I've ever seen.
Why you did it? Why you wanted to see this thing? There is a reason, or?
Why I wanted to see it?
Yeah. Why you were
Or why am I presenting it today?
Or why you were
Well, I mean, one thing I was trying to do was try to prove the same thing for a certain degenerate equation. So since Luca asked, so I was trying to, so does this work for certain degenerate elliptic equations?
In 2 dimensions?
In 2 dimensions. In 2 dimensions.
Okay.
The thing is that the Laplacian is a prototype of a uniformly elliptic equation, right? So all of this stuff works for uniformly elliptic equations too. Of course, you have to prove that uniformly elliptic equations admit fundamental solutions that look like that. That is a non-trivial theorem. That is a theorem of Littmann, Stampacchia, and Weinberger in the divergence form case. In the non-divergence form case, it's also not exactly true. So let's just stick to divergence form examples. I was trying to prove this for divergence, a specific divergence form, but degenerate elliptic equation. And if anyone cares to know, it was the linearized Monod-Ampere equation. I was not able to prove this, mostly because I don't understand the nature of the solution at infinity. The trick would have been to do some kind of Kelvin transform, but it turns out it doesn't really work. I can talk about that some other time to anyone who cares to know. But yeah, that was the reason why I was looking at this proof.
No,
because
why you said it didn't work for because you don't know the fundamental solution?
I don't know how the fundamental solution behaves globally. In fact, I don't know the existence of a global fundamental solution.
Okay.
I know the existence of a fundamental solution on a bounded domain.
Okay, but not globally.
But not globally. One. And even if it was global, I don't have any knowledge of its behavior at infinity. At infinity, it has to do this kind of stuff. For this proof to work, it has to do this. It has to be radial in some sense. 1. 2, it has to go off to negative infinity. So if it doesn't do that, I don't care if I have a fundamental solution because it won't help with the proof. Just like it doesn't help in 3 dimensions.
Yeah, exactly.
So I need, in some sense, if you really want to abstract this completely, I need the existence of a solution to the exterior Dirichlet problem, which has a certain growth at infinity.
Yeah.
Okay.
It has to decay.
Yeah, I mean, well, it has to grow, not decay.
Yeah, whatever.
Yeah.
Minus or plus,
Yeah. So that's what I need, and it's not even remotely obvious that that's possible.
I see.
Of course, I gave up on this technique a while ago. I'm trying something else now. We'll see if that works. But yeah, that was the reason why. Also, I think the proof is just cool, frankly. A lot of stuff, by the way, just to maybe as a sort of disclaimer, not anything that anyone presents here has to do with their research, I hope. I mean, if it doesn't tie to your research, I don't care. I'd like to just see something that's interesting. So this somehow ties to my research, but not really. Well, it was important 3 months ago or so, but not anymore. Okay, so any questions before I move on? There's another proof of this which I don't like so much, but I don't want to talk about it. I'm already running out of time. That's like 1 degree slicker than what I just did. You just make up a function out of nowhere. I'm like, okay, and then it works. So if anyone wants to know, I'll show you, but I don't like that proof as much. Okay, so that was kind of like Liouville type theorem number 1 for me. But in all of these types of theorems, you'll notice that nothing like the Harnack inequality or the mean value property was used. And of course, you can't use it because, well, it doesn't actually hold in these cases. Okay, so this was my first theorem of the day. Second theorem I'll prove is, again, another Liouville theorem that I don't have a name for. So this one you can call, in some sense, the subharmonic Liouville theorem. But, well, you can call it whatever you want. Let me prove a variation of this using a completely different technique. And it's a variation in the sense that they're different theorems, but the conclusion is the same. but the technique also is very, very different. Okay, so here's the theorem. So I'm going to consider now sub-solutions that look like this. So it's not really a sub-solution per se. If you're a non-negative sub-solution, then of course you can throw this guy away, right? So, but let's write it like that to keep it as general as I possibly can. And so consider this inequality, just this inequality in R2. The thing is, this assumed an upper bound, but now I'm going to have to assume a L infinity bound everywhere. Okay. Of course, like I said, these theorems are not the same because, well, this is different from that, but at the same time, this is stronger than that. So, okay. Conclusion is, however, the same. So then U is constant. Okay. Of course, again, everything is smooth. Okay, so don't worry about. You can do this again for weak solutions. You can do this for you can do this for H1 or H. You can interpret this in terms of H1 instead of Laplacian. So everything works. But let's just think of them as smooth. However, that being said, I will simply use the integral characterization of this. I won't. I'll simply jump from this pointwise inequality to an integral inequality, which is really the fundamental philosophy behind weak solutions anyhow. So the proof is going to be...
But if you integrate these things, you Laplacian of you integrate.
This equation has a weak form.
Yeah, I'm thinking. Oh. Okay, go ahead.
And let me write down the weak form. It's like it's just a matter of multiplying and integrating with parts. So. Okay. Actually, before I prove it, I'm going to prove a lemma, rather. And this goes by many names, but since I'm living with 3 Italians, I have to call it Cacciopoli's inequality. Some people call it the energy inequality. Some people call it the reverse Sobolev inequality. Call it whatever you feel like, I suppose. If Cacciopoli is too hard to spell, then there are many options for you that are available. Okay, Caccioppoli's inequality says this, all right? Take any smooth function. So for all smooth, compactly supported function, and of course this is true in Rn. So I'm going to write it as a statement in Rn. I'm going to apply it in 2 dimensions later. You have the following inequality, okay? It's kind of like an integration by parts inequality. And the proof is also integration by parts, basically. It says this. Okay, by the way, and you have to satisfy the inequality, otherwise this is obviously not true for every function in the universe. You can kind of switch the order of differentiation. You can transfer derivatives from this guy to this guy, is basically what the inequality says. Of course, you have to account for all of that with a 4. Big deal. All right? And this is everywhere. So the integral in all of space. Again, these are all compactly supported, so all of this makes sense globally, right? Okay, what's the proof? The proof is, again, an integration by parts sort of trick. So proof of Cacciopoli is this. You simply, and this is a trick worth remembering, I suppose. You have an inequality like this. You can totally conserve it by multiplying it by a positive quantity. So take the square of this function, and this is still true. You agree? Multiply by a non-negative function, so everything is fine so far. All right, now, of course, you can integrate this, right? Integrate this in all of Rn, it doesn't matter. I'm not going to care about boundary terms at all because there are no boundary terms to worry about. Okay? Now, if you... I'm clearly taking up too much space with these things. Okay, so you can take one derivative from here and plant it on these guys. So as long as you also have a minus sign, this is true. Agreed? All right, everything is smooth in my universe, so I'm going to use product rule freely and not worry about it. Of course, that also works in the weak regime. So everything I'm saying here will work. All right, so if you use the product rule, well, you get 2 phi grad phi and a u. So 2 phi u grad phi. And then you throw the derivative on the other guy and you get phi squared grad u. All of that dotted with grad u is not negative. Agreed? Okay. So break this out. All you get is, well, yeah, it doesn't matter. So let me break this out. So you get 2 phi u, grad u, right? Minus phi squared, grad u squared is non-negative. Okay? Any questions so far? All right, so I don't like this guy here. I'll throw him on the other side. Now this guy, the inequality goes the right way. You can use Cauchy-Schwarz, right? So the integral phi squared grad u squared. How do you use Cauchy-Schwarz though? That's the clever part. You pair u with grad phi, and you pair phi with grad u. Okay? What happens then is you get a phi grad u term squared. Yeah? And you get, I guess there's a 2 here. So, and you get a u grad phi term. All of that squared. Agreed? You got to pair things right, otherwise this doesn't work. What was the virtue of pairing things correctly? Well, look, this is a full power of phi squared grad u squared. This is a half power of phi squared grad u squared. Divide, which you can do, of course, because it's not 0. If you divide, then what do you get? So okay, everyone knows what's happening, right? So coming from there, what you do is you simply divide and you get half power of this is less than 2 times the half power of this. Square and you're done. Okay?
So there the only problem is that u is in L infinity. We know only that u is in L infinity. Because otherwise... I haven't touched this assumption yet. No, no, I'm saying otherwise, I mean, there if u is regular, I mean, it's u Laplacian of u bigger or equal than 0. You start...
I'm pretty sure there are counterexamples if you don't assume boundedness. In fact, like I said, x squared.
If you integrate by
x squared is always a good example with these things.
If you integrate by part, u Laplacian of u, no? Take the integral, u Laplacian of u. Integrate by part. What you get is minus the gradient, the modulo of the gradient square. And so this has to be bigger or equal to 0, so this implies that it's impossible, so the gradient of u is equal to 0. You see what I'm saying?
No.
No, because you don't have the phi that you...
Yeah, you didn't pick a phi.
You need a phi. No, okay.
But you're very close. You have to pick a phi.
Yeah.
And the point is you pick the right phi and everything works, okay?
Yeah.
All right, so to make sense of what Luca kind of said, let me simply pick the right phi. Everything here was for some arbitrary phi, right? So let me be clever and pick the right phi. So I'm going to leave this here just because I'm going to need this in a few minutes. So the idea is this, that the phi here, you can make it act like an identity on a ball.
Yeah, exactly.
Right? Yeah. On the other hand, there's the grad phi term, so don't make it act like a characteristic function because then your derivative is going to blow up. So I'll just smooth it out, make it look nice, and everything's going to be fine. That's the moral of the story. Okay? A nice bump function that has a nice bounded derivative. So for the proof of the theorem, I am simply going to pick the right phi. So choose So again, you can do this for each r bigger than 0, of course. So choose a phi sub r that looks like this. It satisfies 3 properties. So the support of phi r is the 2-ball of radius r. Everything's centered at 0. Okay. Phi r is identically 1 on the smaller ball. And you can cook this up so that the gradient is exactly, basically the rise over run kind of thing. All right, so it's r this way and 1 this way, so it's less than 1 over r. Okay, so my function looks like this. So here's the 1 ball, here's the 2 ball, sorry, all the way around. You make this the characteristic function here, but then you taper it off so that it's all nice and good. Okay, and you can always ensure, since this distance here is r, you can always ensure by, let's say, the mean value theorem, that the derivative is at most this guy. Okay? I guess I should also say it's just between 0 and 1. Okay? So don't make it anything funny outside the unit ball either. Just let it go to 0 and let it go to 0 nicely. Okay?
The support is the closed.
Support is the 2-ball. Yeah, okay, fine. Yeah, support is the closed set. I never told you that B2R meant open ball. So, okay, so actually, let me throw up Ketchopoli here. It's easier to. Okay, so I have 10 minutes. All right. So the point is this, that all of this implies something about the support of grad phi r, which also is a smooth function, also compactly supported. But of course, here the derivative is 0, right? It's 1 there. So the support is, in that case, on the annulus. Okay? So the derivative actually contributes nothing on the inside, right? Okay, if you apply Ketchopoli, so by Ketchopoli, you get this. You simply stick phi r in here, and you get the following. Okay. Of course, this is on the annulus, otherwise it doesn't count for anything. This is on the 2-ball, right? But that's fine because it's the identity on the unit ball. So I can totally dominate this integral by that integral. Agreed? Okay, so what you have is effectively a bound on the what's called the Dirichlet energy on an R ball by effectively the L2 norm on an annulus. I still haven't used this, so let's use it. You get a 4 over R squared integral over U squared, integral of U squared over this guy. So that's really what I should have said, or what I should have written before I said what I just said. You can control the energy by the L2 norm on an annulus with a little bit of decay. All right? Okay, I still haven't used this assumption. If you use this assumption, so since this is finite, you can pull it out. If you pull it out, here's what you get. Sorry, it's U. Yeah, thank you. So you get 4 times the thing squared, and then you get the area of the annulus divided by R squared. which in 2 dimensions is simply a constant. Okay? Annulus scales like r squared in R2. This is why this proof completely fails in higher dimensions, unless you assume something a little more. Okay, what was the point of this? This is uniform in R. Okay? So, let R go to infinity, and you get that grad U, I guess the norm of grad U, is in L2 of R2. Okay? This, of course, doesn't prove that it's 0. Simply prove it's integral, right? All right. So let me go back to the proof of Ketchopoli in some sense. So remember that the proof of Ketchopoli worked like this. You have, and I'll apply it in the case phi r squared. So phi r squared grad U squared. Before I applied Cauchy-Schwarz, looked like this. It simply had a U, a phi r, a grad U, and a grad phi r. Okay? This was before Cauchy-Schwarz. Okay? Now, of course, I am free to apply Cauchy-Schwarz now, again, except I'm going to do it better. This is on the 2-ball. This is on the annulus. Because again, grad phi is only supported on the annulus, right? So do Cauchy-Schwarz now. Don't do it like you did before. Do it now with this information. Okay? All right, if you do it now, here's what you get. Same pairing as before. U with grad phi, phi with grad U. Okay? U squared, grad phi r squared on the annulus. Oh, this is a 2. And phi squared with grad U squared also on the annulus. Okay? Now this guy is effectively this guy which I showed was bounded. Okay? So there's some giant constant here that is independent of everything other than the L infinity norm of U times the integral phi r squared grad U squared. To the 1/2. Of course, phi r, remember, was a function between 0 and 1, so I can effectively throw it away. Everyone with me so far? Now let r go to infinity once more. I know this is a function in L2. You see, that was the whole point of doing this first. Otherwise, what I'm about to say will not make sense. If you let r go to infinity now, this is the integral outside a giant ball. So this goes to 0 as r goes to infinity. Conclusion is that this integral, of course you can bound this by this guy, right? So the conclusion is that this, in all of R2, is 0. Take the integral of a positive function. If it's 0, then it must actually be the 0 function. So the gradient is 0.
No, wait. Okay, this goes to 0 as r goes to infinity because you're taking the integral over the...
So again, I can dominate this by the integral outside the ball even if I want.
Outside, oh, so yeah, okay.
Right?
Okay. The other one you say is...
the other one is bounded from below. This is an r, right? The integral on the r ball of the gradient.
Because on the r, yes, exactly, because r is 1 on the r.
Yeah.
Okay.
So if you let r go to infinity in the monotone convergence or whatever, it tells you this converges to the integral in R2. That goes to 0, so the integral in R2 has to be 0.
Exactly.
Okay? Which of course tells you that grad U is constant. Well, sorry, U is constant. So grad U is identically 0, so U constant. Okay?
Okay, you have that gradient of U is in L2.
From here, from this part of the board.
and there you are using this. You are dominating these things with this. Ah, okay, I see. Okay, yes.
Okay.
Good, yes. Done. Yes.
All right, so any other questions on this proof? So I'm out of time. I could have shown one more application of this, but I won't. What I will do is, however, mention that none of this really relied, as I said, none of this really relied on the structure of the Laplacian. It relied, well, it didn't rely on the pointwise nature of the Laplacian. It depended on the structure of the Laplacian. So all of this actually works for more general divergence form equations like this. So you can put a little bit of a bounded function here, and you can get the same kind of theorem that the u is in fact constant, right? So the proof is almost identical. You just have to make sure this guy sticks around in the right places and doesn't disturb anybody, okay? And after that, the proof still works. Why would this be important? This version was used in the proof of what's called the de Giorgi conjecture. And since I'm out of time, I really won't say what that is, other than the fact that it's another kind of Liouville theorem that was an open problem for a while. But it turns out tricks like this could actually get you to the proof of that theorem. All right, I think yeah.
So where did you find that little gem?
Which little gem?
The one that you just proved. Where's that theorem from? Is it like a reference?
Oh, you mean this theorem, the u Laplace u?
Yeah.
So yeah, if you look at, okay, right. So this was proved, so the de Giorgi conjecture was proved So it turns out so for the n equals 3 case, it's by Luigi Ambrosio and Xavi Cabré. Now the point is that this proof is actually harder in 3 dimensions. So I only mentioned the 2-dimensional case because it's significantly easier. But if you want a proof of this, you can actually find it in that paper. Just ignore the 3-dimensional aspect if you want, because it's a little more subtle in 3 dimensions. You have to prove some more stuff. But yeah, other than that, it's really a 2-dimensional trick here at the very end. The thing is, if you, on the other hand, assume some growth of u squared over r squared, then the same kind of theorem holds. So then you have to come up and prove that u actually, if it's a solution to a PDE, it decays like that, and then you're fine, basically. Okay? All right, I think that's it for me and for this entire talk.